for the webinar series based on frontiers in artificial intelligence from automation to societal applications conducted by the Data Science Research Group of IIIT Kottayam. IIIT Kottayam being an active organization for, de- for dealing with and the current day technologies like data science and artificial intelligence on having observed the importance and growth in this tech field have been great enthusiasts in organizing this webinar and parting the knowledge and usage of the advancement of artificial intelligence through this. So we officially bookmark the beginning of the event with a 1 minute silence. Now, I call upon Dr. Christina Joseph, ma'am, to address the audience regarding the overview of the event. Over to you, ma'am.
Thank you, Ram. A very good afternoon to everyone. The American multinational fast food giant KFC, Kentucky Fried Chicken, goes by the adage, it's finger licking good. Similarly, artificial intelligence, commonly known as AI, is on everyone's lips now. In the Union Budget of India 2022, the Honorable Minister of Finance, Srimati Nirmala Sitharaman, emphasized the need for sustainable development by leveraging the technological advancements like AI. The past decade witnessed a surge in carbon emissions from vehicles, which led to the pressing need for manufacturer obligations and government regulations. The current era demands the rapid pace of technological developments to be paralleled with carbon emission mitigation strategies. Google Research is one of the leaders in this movement and identified the 4 M's: best practices to reduce energy and carbon footprints in a public release earlier this year. All this calls for massive efforts to be directed by every stakeholder of the AI lifecycle towards reducing the carbon footprint. As the first step towards this, the Data Science Research Group, IIIT Kottayam, presents Webinar 1 by our respected and renowned speaker, Sri Anmol Krishan Sachdeva. This session is the pilot webinar marking the launch of the webinar series on Frontiers of Artificial Intelligence from Automation to Societal Applications. The upcoming webinars will focus on critical cross-cutting directions posed by AI. We hope that this webinar series helps each of you to accelerate your AI journey. Over to you, Ram.
Thank you very much, ma'am, for having given an overview about our series to the audience. Not wasting much of time, I take great honor in introducing our speaker for the day, Mr. Anmol Krishan Sachdeva, who works as a hybrid cloud architect at Google. Sir, being a great enthusiast in the field of innovation and dealing with new current day technology, has completed his master's in advanced computing from University of Bristol, United Kingdom. Mr. Anmol has done some of the most prestigious conferences like EuroPython, GeoPython, and PyCon India. Mr. Anmol Krishan Sachdeva, known as Great Devox, being an international tech speaker, is also a great tech panelist and has represented India at several reputed international hackathons. He is a deep learning researcher and has about 8 publications in different domains. Now, I welcome you, sir, and I also want to thank you for accepting this invite. The platform is all yours, sir. Thank you. And participants, there's a note here. All the queries would be addressed at the end of the sir's talk. And as sir finishes the talk, you can start posting the queries in the chat box. Thank you. Over to you, sir.
Yeah, thanks a lot for the great introduction and also for inviting me to this forum. I really I'm very excited for this talk, and thanks Dr. John and Dr. Christina for giving me this opportunity. So without further ado, let me start sharing my screen. I'll take over the control. Uh, okay, let me know once it's visible.
Yes, sir, it is visible.
Great, thanks. Okay, so good afternoon, all present. We are here to talk about towards green AI, which is kind of seems like a practice or an endeavor to have the carbon curtailed, the footprints of carbon reduced when you do Python coding in AI. And ultimately, we are going to see the CodeCarbon package through which we'll be able to exercise all of this. So before starting the talk, let me further add on a few things regarding my background. So as mentioned, I'm a tech speaker and I have spoken at various conferences like KubeCon, PyCons, different Python specific conferences like EuroPython, GeoPython. And I have also contributed actively in organizing the Python conferences. And we have one conference going to happen in the coming week as well, which is EuroPython. There also I'm the organizing member. Additionally, I'm very much inclined towards research and like to mentor people, and my interest lies in emerging technologies like computational neuroscience, computing, kind of high performance computing, quantum computing, and even deep learning. And based on this, I have done some research as well in the past and have around 8 publications in international journals. Talking specifically about my work at Google, I'm very much into architecting and building large scale systems for hybrid and multi-cloud solutions. I'm also dealing with some sort of distributed systems and work closely with site reliability engineering and emerging technologies. One disclaimer before we move ahead, the content of the talk is something which is my own work and should not be related or associated with the work of organization or any sort of organizational initiatives that are there by Google or any organizations I'm associated with. So this is purely work of research, and I'm not the maintainer of this package, but I'm an active user of this package, and hence I want to spread word in the community regarding same so that the budding AI and data scientists and the machine learning, you can say, enthusiasts can leverage this and contribute to greener AI. Okay, so the flow of the talk is as follows. We are going to understand what CodeCarbon is, what carbon footprint is. We are going to see how compute and coding contributes to carbon emissions. We'll then have a look at the package itself. So we will go ahead and we will have a short demo, which will be followed by the, you can say, visualizations and demonstrations. We will see how reporting happens and how we are able to make decisions with respect to the code execution that we do. So let's understand the concept of carbon footprint first. So carbon footprint can be thought of as the total greenhouse gas emissions which can be caused by an individual. So it could be an event, could be an organization, a service, a place, a product, and is expressed as carbon dioxide equivalent. Since we are here to talk about controlling carbon emissions of AI Python code, let's understand how the code and related computations can contribute to the carbon emissions. So we all know that organizations around the world are heavily investing in MLAI research, distributed systems, IoT, even connected components have started emerging. There is high performance computing, and there's a lot of stuff going on with respect to emerging practices. And all of this stuff requires good amount of power or electricity in general, right? So more computing power actually means more impact on the planet. And this is what we are going to see and learn during this session. According to some published research, which is linked below in the right section of this particular deck, data centers consume 1 to 2% of total energy generated worldwide each year. Okay, so this is a good amount, a huge amount, right? Moreover, the energy used by these data centers has doubled over the past decade and will likely triple or even quadruple within the next decade. So this is an area of concern for all of the engineers that are working towards AI and high performance computing systems. You'll be amazed to even know that the number of compute instances, the cloud compute instances that we use has grown by 550% over the past decade itself globally, which is again a huge number. So 550% is a really big number, right? So before we move on with the actual stuff, let's understand another term which we should add in our vocabulary, which is carbon intensity. Okay, so carbon intensity of computing is directly related to the quantity of source of electricity being used. So it could be tidal energy, could be wind, fossil energy, and so on. And we will see some energy patterns as well and their comparisons in the demonstration that we will be having towards the end of the session. And it is measured in grams of CO2 equivalent per kilowatt hour of consumption. And this is something which we are going to use in our demonstrations, and we are going to reference this concept of carbon intensity every now and then. Okay, so let's look at some factors influencing the carbon intensity so that we form some good foundations and we try to understand what all impacts the carbon intensity. So energy sources are the first, you can say, is the first factor. It could be coal, petroleum, hydroelectricity, tidal natural gas, and depending on the energy source, the carbon intensity fluctuates, right? The cloud region is even something which is an area of great concern, because ultimately it is the region where the energy source is getting defined. So it could be that you are not somewhere near coastline, or you don't have access to sea or ocean, or maybe any hydro plant, and you are hence using coal or petroleum. So cloud regions or cloud server regions even have impact and influence the carbon intensity. Then there is compute time. So with high compute time, naturally you will be using more number of resources, and hence you will be having more carbon impact. But we will see how we can optimize this and how we can tackle this thing. And then hardware can be CPUs, GPUs, TPUs. And essentially we have seen that with growing AI stuff and trends, people have started using GPUs and TPUs, and they have even started building models with billions of parameters. And because of these parameters, they need to do hyperparameter optimization as well. And all of this results in much more computation, which ultimately is resulting in more carbon emissions. So this is a graph which is representing the grams of carbon dioxide equivalent compared to the amount of carbon sequestered by trees and the emissions from a car in Europe. I'll explain you this graph. Let me show the pointer first. Okay, so on the x-axis we have the carbon footprint in grams of carbon dioxide equivalent, and on the y-axis we have the models mentioned. These are 4 models. First is irradiation simulation of DNA. Then there is weather forecast with ICON model. Then there is weather forecast with IFS model, and then there is NLP BERT. And then on the right-hand side, on the x-axis, you see the comparison made with 3 months, and which means the number of or the amount of carbon sequestered by trees. And it's basically shown in power of 10. Likewise, the distance traveled in a European car in terms of kilometers, which is again shown in power of 10. So we see that the first example shows the simulation of effects of radiation on DNA. And to train this model, if we have a single run, which is highlighted by the green color here, it is taking it is generating some carbon footprint, and we have close to 10 power 2 3 months equivalent of carbon footprint getting generated, or it's even equivalent to 10 raised to power 3 kilometers, which means 1,000 kilometers traveled in Europe by a car. And if we see the orange graph, that is ultimately the PSF, or when the same task is executed multiple times, how much of carbon is being sequestered or generated, right? So this is equivalent to 10 power 4. And ultimately, we see that NLP BERT, which is one of the most common training models out there and very popular as well. If we are using this, it is going to generate 10 power 5, which is 100,000, equivalent to 100,000 kilometers traveled in Europe, which is a very, very big amount, right? So this is the impact which we are showing. And being AI researchers, we do tend up training the models every now and then, and we forget to pay focus on how much of impact we are having at the environment level. But ultimately, this graph actually shows that this is a huge impact which we are creating, and ultimately it's a negative impact. So we should do something in order to curb this out. So this is something which we need to understand, and let's move to the Python aspect of it. Python is a programming language which is very popular with the AI community. And ultimately, we need to understand how Python is impacting the environment. Ultimately, it's the code which is of concern, and how we run the code is of concern. Where we run the code is a concern, and what electricity source is there which is powering the computations is a concern, right? So all those factors which we saw in the carbon intensity factor graph, all of those factors are here to play. It is interesting to understand that optimizing the code actually makes it run faster, and eventually you will have lesser emissions produced. So by optimizing your code itself without changing any of the other parameters or factors, you will be able to have less carbon emissions produced, right? And it's also interesting to know that carbon emissions even vary depending on the underlying programming language. So let's say you are coding in C++ or you are coding in Python, then ultimately it depends how much of carbon is being generated by C++ and how much of carbon is being generated by Python. And we will see such comparisons in the later slides. Python generally takes a longer time to run and produces more emissions. Why this is the case is because effectively Python is a language which is single threaded. Okay, why this is single threaded is because the concept of global interpreter locker. This is the GIL or GIL interpreter locker, which is a mechanism to manage memory effectively in Python. And ultimately, because of this, we don't have multi-threading executed in Python, the base implementation at least, which is a C Python based implementation. And we have a few workarounds like using multiprocessing, which can be used, but then it's not effective. And ultimately, this results in the code being produced as an ineffective unit, and we have more carbon emissions created. So this is a graph which we see, which is showing the comparison of the same code or same program or same code block or model trained, which is the n-body simulation. And then when I say n-body simulation, it's a very popular model which is trained and which is used by physicists for atomic particle simulations. So they simulate n number of atomic particles, and ultimately they see what's their impact, and they analyze that. So when we have this kind of a simulation done, it's very costly, very compute intensive, and ultimately we are just doing n-body simulation using different programming languages to understand how they result in carbon emissions. We see that Python is at the very very top on the right hand side, and this is CO2 production versus time to solution. And this is just showing that Python took a very long time to run, and ultimately it resulted in more CO2 being produced, right? Now, how to tackle this problem? And then you see that its comparison is made with Java, Ada, C++, Swift, and you see like C++, if we take, for example, it is taking a lot less time, which eventually is producing less carbon footprint, right? Now, this graph on the second slide that I am showing is in contrast to the previous one and shows how Python code, if optimized, can help in reducing carbon emissions. Okay, so here we see that some variations of a Python code outperform even C++, which is in contrast to what we saw in the previous slide. The most standard way to execute Python is to interpret it with the reference implementation called CPython, as I have already told, and CPython is the base or the default reference implementation for Python. And to discuss about CPython in this particular talk will be beyond the scope, so we will skip the details of CPython as such, but I'll still cover some of the overview so that you are able to understand how the underlying interpreter is also impacting and the carbon footprint and the quality of code and the optimizations, right? So lack of JIT compiler or just-in-time compiler in CPython is relatively slow. Okay, so we need to see some alternatives which can be used in order to have our Python code made performant, right? So some interpreters compile parts of code during execution, as I mentioned, which is just-in-time compilation or JIT or JIT compiler. But we know that dynamic languages like Python can also be compiled ahead of time using AOT compilers or ahead of time compilers. So in this particular experiment, if you see on the screen, this is using something called Python. This is using PyPy, this is Numba, this is Python again. And then we have C++ standing here, and we see that 3 of the variations of our Python implementation are actually outperforming the C++ code execution for n-body simulation that we did, right? Why this is happening is because specifically talking about these. So Python, it's an AOT, so Python NumPy AOT compiler that ultimately transpiles to C++. And this is why it is performing better than the native Python code that we saw earlier in the previous slide. Then there is Numba. Numba is again a Python NumPy JIT compiler instead of AOT compiler, as Python is, it's a JIT compiler, and it's based on LLVM, the same compilation target which is used in languages like Julia, so it is comparable to Julia. Okay, and then we have PyPy, which is an alternative Python interpreter with a built-in JIT compiler. So this is something which is standing out here, and we see that Python actually outperforms very well C++. The area to focus or the thing to learn here is that inefficiency of the interpreter has a weak impact on the overall performance of the most of the programs, since total elapsed time and the energy consumption are often dominated by computations that are done by these optimized libraries, right? So we need to understand that we can optimize, but still there are factors like energy consumption, time elapsed. Ultimately, we are trying to minimize those using these optimizations. But the main factors which are influencing the carbon footprint are the time and energy consumption that are a result of inefficient coding, probably, but it has indirect relation to the interpreters, right? Before we begin to look at the CodeCarbon package, let me call out some facts, figures. The number of floating point operations per second, which is also known as flops, you all may be aware of, which actually is a measure of computing performance, has steadily increased by a factor of 150 since I would say like 2004 or 5, and it was close to 100 gigaflops in 2004-5, and it has increased to 15 teraflops, which is like 150, an increase by a factor of 150, and it's a tremendous increase. And this is just because of the GPU models being exposed and being practiced here in every now and then, right? And the same thing which I would like to tell again is something which marks the trend of where we are going. So let's say we again pick an NLP BERT or an NLP model which is trained using, say, neural architecture search. So that can emit more than 600,000 pounds of CO2 equivalent, which is like 6 lakh pounds of CO2 equivalent, which is about 5 times the lifetime emission. I'm stressing here, lifetime emission of an average American car, right? Which is very big, right? So we need to understand that this situation is serious, with the number of AI engineers, data scientists, ML engineers, people who are interested in high performance computing, or even computing which is on the lines of quantum computing, which is another game itself. We are ultimately impacting our environment, and we need to be very cautious and mindful with our next steps, how we proceed with this, so that we don't impact the environment, right? Okay, so yeah, so CodeCarbon is an open source Python package. It can be installed using pip or conda, and carbon emissions tracking is based on the power consumption and mainly the location, which ultimately influences the carbon intensity, as we have seen. And this has seamless integration into Python code, so you don't need to modify or rewrite your Python code from scratch. And this is the main advantages of this library. There used to be some emission tracker and emission usage library in Python, which just worked on very fundamental power consumption stats. That is no longer being used as such, but that was the library which started this, and ultimately we have something sophisticated, which is CodeCarbon, and this is something which has been built by the Mila Institute at Quebec, Canada, along with some other associations with some neighboring institutes and universities in Canada, Montreal. And this package is something which has changed the way people have started thinking about AI, because now people are aware that they are creating impact which is negative on the environment, and they should be doing something, or at least reporting how much of carbon emissions are being generated by them when they run their models. And people are being considerate that we should be running the stuff in a very strategic manner so that there is less impact on the environment, right? And another good thing about this package, and this is something which academia as well would benefit from, is that it provides estimation for both cloud as well as on-premise or private data centers, right? So it could be your laptop, it could be your institution cloud data center, it could be your institution private data center that you have on-prem. So it works well with all of those, and there's no restriction as such. So let's get started with CodeCarbon. We will start with installing the carbon package. In this particular demo, I'm not going to show that because it's a simple pip install, so we will be skipping that in interest of time. You can check out the official documentation for the corresponding steps that need to be followed for installing the CodeCarbon package. We're going to embed the CodeCarbon, you can say, package in the Python code base for MNIST, which is like digit classification problem, and I've kept it small so that we take less time in training, and I can do some training rounds even during the talk. And then we will run the code and we will see how much of carbon emissions are getting generated, and we will track them. We will also see some fancy visualizations which will also recommend you how to modify the way you are deploying your code or deploying your model or whatever it is in cloud or maybe on-prem, and it will show some nice comparison, and we will see that in a detailed report towards the end of the session. And then ultimately, it's not going to give you optimization recommendations for what you should do with your code as such in terms of, say, function optimization or class optimization. No, it is going to tell you based on the factors that we explored during the start of this talk, like the energy source, the region where you should be running it, whether CPU or GPU should be used, right? And ultimately the electricity source that is there. So let's see from static analysis. Let's do a static analysis on how CodeCarbon package can be incorporated in your existing in your existing Python code, and then we will look at a real demo. Okay, so this is the first mode, and this I'm calling as online mode or online one, just because we have a segregation for how the code should be embedded or incorporated for you can say models, or for code which has access to internet or hardware that has access to internet, versus how it should be done for private data centers which are having restricted access, which means there's no internet access and the code cannot interact with any way with internet, right? So this is the online method which works well with cloud machines, which works well with your laptop, any machine which has, or any you can say platform which has access to internet, so that the code will be able to make some API calls in the background using this library and will be able to fetch results from the CodeCarbon repo, right? So this is the first online method, and we have two more online methods of how to incorporate CodeCarbon package in your existing Python code and leverage the CodeCarbon tracking. So first is embedding CodeCarbon. It's as simple as importing a library CodeCarbon, specifically the emissions tracker class. And we are going to see in our demo the emission tracker class only. And then you have emission tracker initialized. You start. Between start and stop, this is just telling when I need to start tracking and when I need to tracking. Between these two lines, you put your GPU intensive code, or the code, it could be CPU intensive as well. It doesn't necessarily need to be an AI or ML code. It can be a compute intensive operation, a general core Python program, which is non-AI ML as well. But mostly we have seen people leveraging this for AI and ML studies. A second method is CodeCarbon decorator. So instead of using that tracker start and stop, what you do is you just decorate your training loop with this track emissions decorator. So this is again a straightforward thing. You don't need to do anything fancy. You can have your code, existing code, stay as it is. Just go ahead and have the tracker added to the main function that you are going to execute, right? This is very intuitive. And then CodeCarbon Context Manager. This is a relatively new way of adding CodeCarbon or incorporating CodeCarbon in your Python, existing Python code. And ultimately, how it works is it works on the concept of runtime context. So what you do, you use the emission tracker class itself, but you, instead of importing and using the tracker start and stop functions, or by using decorator, what you do is you create a runtime context by using with emissions tracker as tracker, and ultimately you just put the code beneath this, and once it runs, it actually does all the functions that are expected, and it's just setting a runtime context for your code and wrapping it up with the emission tracker class. Then this is the offline method, and this is the first offline method. What changes here is that there are less number of calls being made ultimately, and where the call minimization is happening is since you don't have access to internet, the calls won't be made to the CodeCarbon repository or registry wherever it is having its data sources and the related data sets defined. Ultimately, what you do is, and there are multiple arguments, you specify the arguments like country code, and this is something which you can find in the references, which country code to use, and the associated mappings. So you actually pass in the offline emission tracker class, you pass these arguments. So you are defining that, okay, I am based out of Canada, my energy source is hydropower, I'll do this thing. So you actually specify all those constraints using the arguments, and generally people use the region argument only, but you can go and check out the other arguments for which the reference is provided at the bottom. And ultimately you just follow the track start and stop, so it won't make any calls to the data sets that are publicly available for the CodeCarbon package. Instead, it will rely on the inbuilt data that it has, and that data is again up to date, but you will to kind of keep on updating the packages, the library, for fresh data and stuff. So be very sure that you are not running it on some stale library version which is probably deprecated, because then the estimates that you get will be ultimately off, right? So won't those estimates would be stale, so you won't want to work on stale trends, right? You will always work on the latest trends that are there. And second thing is, again, in the tracker emission decorator itself, you pass offline mode as true and you pass country code, and it's very similar, and it works flawlessly. So let's start getting into the demo, and ultimately all of you can actually access the files for this particular repository, even the slide deck and the associated code and other additional references that will help you learn CodeCarbon package and ultimately start utilizing it, right? So tinyurl.com/IIIT-codecarbon is the link. You click on this link, or you maybe type on that, and ultimately you will have a Git repository where all these resources are committed, and that repository will look like this. So this is the deck,
Dear
and
Anmol,
link to
can
the
you
deck has
share
been
that over
specified
the
here.
chat box?
This is the MNIST implementation that we are going to go through. So let me open that MNIST implementation. And let me expand the font size. So ultimately what we are doing is, or let me switch to, I think I can switch to my code editor, and from there I can take you to live demo as well. Okay, so is it visible? The font size is readable, the code? Okay, I believe it is. So let me type it out. tinyurl.com IIIT CodeCarbon. I'm typing in chat as well, so you can access the resource and go through the code alongside. Okay, and probably if you have the TensorFlow setup, you can even execute the code side by side. Okay, so basically first thing that we are doing, and I'm going to break down this code, and for the next 5 minutes we are going to stress on this code, and then we will visualize the results which has been generated. And this is just a sample implementation that I'm going to run with a less number of epochs, but I have trained the models on different machines, one in cloud, one in my personal Mac, and we will compare and contrast between the results, and we will get to know how we are able to leverage the module, right, and how we are able to imbibe the deductions or the recommendations that we get from the module from the module in our day-to-day work. So let's get started. So first thing, at line 2, I'm importing the TensorFlow package and I'm AIML or deep learning or Keras library or TensorFlow perform different customizations or actions at various stages of the model training. It could be towards the start of model training. It could be towards the end of model training. Could be when to stop the model if some condition is hit, or could be even during epoch, during start of epoch or during end of epoch, what we need to do, right? And we will be leveraging some of the functions that are there for the callback, and we will see how we are able to leverage that. And then ultimately, this is the CodeCarbon import that we are going to use, and we are going to use the online mode one, which is emissions tracker. Ultimately, this code will show how we can use the Keras callback to save emissions after each epoch. Why this is done is something you will understand, and you will be able to relate once I'm done through the code run, right? So what we do is at line number 12, we have a class definition, which is CodeCarbon callback. We pass the callback object here, and ultimately it has two functions. One is init function and one is on epoch end, which means it will be called at each epoch end. Okay, and we are having CodeCarbon tracker initialized. So self initialization is done for CodeCarbon tracker. How? Because in the callback object, we are passing the tracker that we have for CodeCarbon. So ultimately, it will make it as part of the training. And for each epoch, we will be having this tracker initialized, and we will be having the tracker start and report the emissions for that particular epoch towards the end. Then we have on epoch end, and we are using CodeCarbon tracker.flush. So CodeCarbon flush is basically for registering the carbon emissions for this particular epoch. In general, if you are not using the flush package, right, flush API, what will happen is that, and this is the general behavior of CodeCarbon. CodeCarbon executes, and it only outputs a CSV file, and the CSV file actually looks like this, wherein you have timestamp of run, you have the project name which you are running, you have the run ID, then you have the emissions, you have the CPU power, GPU power, RAM, energy, related, like which country code was there, which particular region in that country, whether it was a cloud provider or whether it was on-prem, what was the OS detail, right? Which version of Python you were running, what was the CPU count, how many number of CPUs or GPUs were there, what was the model of CPU, whether it was Intel, it was AMD or something else, in Intel, whether it was Xeon or it was something else, right? And just I'll be calling out a few things that CodeCarbon package works well with Intel related chipsets. With AMD, you can try out using the Intel Power Gadget, you can say, extension. So you will need to download that software piece, and you can try out, because there's no native support for AMD as such. And even with people who are going to use it in personal capacity on Mac M1 chips or M2 chips, I would suggest that you go ahead and give it a try. The Intel Power Gadget, you give it a try, because that will be able to simulate that kind of power consumption pattern, and you will ultimately be able to have that Intel thing bridged, because Mac M1 or AMD are not Intel chipsets. So you can use that Intel Power Gadget as a simulator, or as something which aids you to carry out the CodeCarbon package related stuff on your computers or machines which are non-Intel machines, right? And then number of GPU, the GPU model, for me it was Tesla T4. The longitude, latitude, since it was internet, it was able to fetch that, the RAM utilization, the tracking mode, and whether it was on or not. So this was not on cloud, this was on my personal, right? All these stats you get, and this is a CSV file which gets generated generally towards the end. So by default, it is a behavior that this file will only get generated towards the end of training. So when you have the tracker stop, this CSV file will be generated. But we want, after each epoch, the callback to return and register these trends. So what we do is we use a special function, which is a new API implementation of CodeCarbon, which is called flush. And we utilize it to register the results after each epoch, instead of having those generated after track stop, right? So what we do, we have done this class definition, then we get into the MNIST code. So I'll just quickly go through it, because it has less to do with what we are trying to achieve today. MNIST is a NumPy dataset for testing purposes, and it's a very common digit classification, which has 10 classes and 2 classes, and it should be used to have digit classification done, not 2, sorry, 10 classes. And then you have the MNIST data, NumPy data split between train and test sets, right? So this is something which is how we define this in Keras TensorFlow framework. And then we actually perform some normalization scaling of images so that we can feed the data in correct form. We have the model building flow. Again, I'm not getting into details of model building because we have to focus on the CodeCarbon aspects of this particular code. So this is like a sequential model build that we have, and there are flat and dense and dropout layers for this particular thing. So it's a very minimal implementation of sequential model and model building for our MNIST dataset. We define loss function, sparse categorical cross entropy, just a very basic function for classification problems. We compile it so that we have a computation graph and the layers, and then ultimately we get into training. So this is important. We have the tracker enabled, okay, or initialized, and we have the tracker kind of stopped. In between, we are doing the callback initialization, and this is ultimately going to pass the tracker that we form here on 52. It is going to pass it to the callback function. This is going to class, and this is going to have it passed in the associated functions. And on each epoch end, this is going to get triggered, right? And ultimately, we run the model fit, which is the actual training. And here, a thing to note is, apart from the epochs, the train model, the X and Y train sets, what we pass is we pass callbacks, and in this list we will pass the callbacks, right? We have CodeCarbon callback here. You could have had multiple callbacks apart from CodeCarbon or in addition to CodeCarbon as well. That is up to you how you want to have the callbacks associated, and this is specifically how we do in Keras, but similar thing can be found out for PyTorch. Even you will see that CodeCarbon is being used by transformers that are there in Hugging Face. So that is something you will see this package is getting quite a good traction in that area, and even people are using it widely. And then you have the tracker stop towards the end, which will stop the tracking, and ultimately it will report the emissions, but we will have the CSV file being built along the line because of this flush function, right? Now let's get into, and I'll run this. So MNIST flush, I run this and I'll get some output. For this particular set, I'm just doing 4 epochs because it will just run in very short amount of time. But ultimately, the reports that I'm going to show you will be for more number of epochs. So I think I ran it for 200 or 300 epochs, and I ran it on 2 different systems, one in cloud, one in personal capacity. And we are going to analyze how things happen. So this is the first epoch being done, and I think under 1 minute we should be done with this particular training. So let's wait for this training to complete. Okay. 1 second, almost. So by the time the epochs are running, let's go through how it starts. So it sees, it starts tracking the RAM, it starts tracking whether it's CPU, GPU, and which model of CPU, GPU it is. So it says Intel Core i7 and something. It says my platform is Darwin Mac. My Python version is this. I have available RAM as 16 GB, and ultimately I have CPU cores as 12. And then it starts the training, right? So it runs after each epoch. What it is doing is it is giving me the RAM power, giving me the RAM energy consumption, giving me the accuracy of model, which is of least concern to us because we are mostly focused on energy consumptions, and ultimately how much of carbon is getting emitted, right? It is going to just collate that and show towards the bottom. So if you see, you have something called as emissions towards the bottom, and I'll expand and zoom in. You see, you have 0 something kg produced just by running 4 epochs of this particular code, and we are able to see how much of electricity consumption, power consumption, CPU consumption, energy consumption was there for this particular training for each epoch, right? So this is the data which we are getting. Now let's get into, and I'll show you reports for the larger sets of model which I have trained, so 200, 300 epochs and different clouds. So what we'll do is CodeCarbon has a CodeCarbon visualization package which comes from the source, or if you are installing it using some manager like Brew or apt-get, you will get CodeCarbon or Carbon board, okay, as the package. But I'm using it as a source build, so I'm going to utilize the source Python file directly. And then you need to supply the CodeCarbon example, the emission. So this is the example emission. Let me first show you the emissions from my own computer, and then I'll show you some bigger reports that are there publicly available. So let me show you. So I ran this in GCP cloud region, US Central one, and that is Iowa. And I have the emissions generated. And what I'm going to do is I'll just route it to my 8050 port on local machine. So once it gets started, I can access these reports on localhost 8050. So let me do that. Simultaneously, let me also open a parallel tab, and I'll open another report to compare between these two. And and I'm going to open the training results of the training that I did on my personal computer, which is this MacBook. So you see, this is the first report, and we have the other report as well live. Let me open that 8051. And let me zoom in a bit so that it's easy for you to understand and relate, and let it load. Okay, so you see, this one is for 8050, which is the Iowa implementation, and the other one, which we see, is the local implementation on my MacBook. So net power consumption, it is reporting that it was 1.8 kilowatt hours, and net carbon equivalent was 0.2 kgs for 200 epochs that got generated. It was able to automatically detect that it was in Iowa. Okay, this is the power of the online system. It was able to track the longitude, latitude of the data center as well, and ultimately it shows us that these 0.2 kilogram equivalent that we have got, right, it is equivalent to 2 hours watching 2 hours of TV on 32-inch LCD TV, right? You can just relate, and you can compare that how much of production I'm doing. Likewise, for larger data sets, so for larger carbon emissions, we should see the miles driven. And for that, let me open another sample data set, and this is something which I'm going to use from the public data set now. It's not something which I trained. The other two are the ones on which I trained. Let me open. Let me open on 8052. So 8052. Yep. So here you see, like, we have multiple projects, and these projects have been run in different regions, different cloud regions, right? And ultimately how their energies compare is something different. So this is in Ontario, Canada. And then we have, say, Brazil. So we see the same model run in two different regions is producing different carbon equivalents, right? So it is 99 kg with 95 kilowatt hours in Brazil, but it's in Canada, it's 120 kg and 113, which means running the same code in two different regions can have impact just because the carbon intensity is influenced by different factors, right? So this is the first example. Let's drill down further. And before that, let me show that 120 kg of carbon equivalent is ultimately 293 miles driven in car, or 74.73 weekly household emissions of carbon that are done in American households, or 52 days of watching 32-inch LCD TV, right? So it's a very good intuitive thing, and you will be able to measure it in that particular manner. And let me quickly go down. So this was my first run, which I did in the Iowa region of Google Cloud. So it has automatically detected that it was Google Cloud. If it would have been AWS or Azure, it would have automatically detected and shown AWS or Azure likewise. And it's showing that the region that I have, if I would have run it in some other particular region, so instead of Iowa one, if I would have, and Iowa is US Central one, if I would have run it in US West one, my carbon emissions would have further decreased, right? So this is giving me an indicator that, okay, if I were to run it in US West one, the same code, it would have generated this much percentage or this much kg of carbon as compared to what I have here when I'm running it in US Central one. And it could have been the poorest if I would have run in Asia Southeast 2. right, which is Indonesia. And then once it does this, and likewise on personal one, you will see that it is not showing the cloud region, but it's showing me some global benchmarks, and we will get to it. It's showing us that, okay, this is a recommendation. Had it been built in US West 1, you should have got 0.0 kg because it's very minimal carbon footprint that it is generating. Then again, it shows global footprint, and it shows that, okay, you can analyze it. So if it's towards the orange or amber color, it means you are generating more carbon. If it's towards the dark green or solid green, you are generating less carbon. And then you can filter it as per the energy source as well. So if it were to be a fossil powered data center, the things would have looked like this. But if it were a hydroelectricity powered data center, the things would have looked like this, which means using hydroelectricity would have given you much more control over carbon emissions than the fossil fuels. And where these electricity grids are placed, where these are available is also getting shown by this particular heat map, right? So this is very intuitive. Again, you can make choices, and ultimately you can drill down and see even between different regions in US how the things are changing. So if you were to run in, say, Oregon, it would have produced 0.24. But if you would have run in, say, Wyoming, it should have generated much more, which is like 3-4 times, which is 1.6, right? All this thing you get with this particular report, and ultimately you are able to see with your training how this carbon emission started, right? So you may have in your training some idle spots, or some could be if it's not an ML training, or even like some core Python training, it could have been some deadlocks somewhere, right? How it would have impacted, at which point it would have impacted, how the carbon emissions it should have shown here. And then you get some emission details as well, and you can get some interesting reports and how to visualize these better on the links which have been provided. And this is for the local run that I did, and you will get a similar kind of data here, but you see the graphs have changed because this was on my local machine. So there was certainly some deadlocks or something which may have happened, or some dynamics would have changed. And likewise for the other sample data sets, you see that there are crests and troughs for emission details. So this means that if you are running on large data set, there will be highs and lows, but ultimately you will be able to analyze how the training goes, right? So this actually wraps up the demo part of things. So let's get on with the rest of stuff. So noteworthy points, as I mentioned, flush function can be used, or the API call can be used, because ultimately CodeCarbon is writing all the CSV data towards the end of training, if not explicitly mentioned to use the flush function. And then some key takeaways, that inefficient coding can cost a fortune. It's not just in terms of money, but the planet itself. So operations must be optimized. You should think about your code twice. You should actually see how you can further optimize the underlying interpreters or the compilers so that your code actually runs. And this is something which, regardless of whether you are using Python, should be a key thing that you should be following. Through this talk, the main motive was to just make the community aware that how the AI trends are impacting the environment, and how we can do a few things on our end which can help us curb this, or maybe reduce this impact which is happening on carbon, or slow down it, right? Ultimately, the trainings would go on, and we cannot have the training stopped, right? But we can optimize how they are done, and we can make some good choices which are in favor of environment, right? The other thing is CodeCarbon provides estimates. So these are based on the data sets which are being updated regularly at regular intervals, right? The remote data sets, the local data sets, different sources are there. Like they need to collaborate with the cloud providers to get the data for the sustainability sector that the cloud provider is running in. Ultimately, it's that these are estimates. So this is good to show you trends. These are not accurate values, because still there is a lot to be done from an accuracy point of view. And moreover, when the CodeCarbon package is running, right, it relies on the RAPL implementation in Linux. So RAPL implementation is running average power limit implementation, which writes the power consumption for the whole machine in a file, a RAPL file in the Linux. And ultimately, it's not having a process level segregation done, because of which, again, it's an estimate. So it's, if you are running multiple training models on the same machine in a shared mode, this is a tricky thing to crack. And CodeCarbon is working on sorting this out by using a package which is called Scafender, which is a Rust implementation. And this is a per process consumption tracker, which is there in Rust. And these people are trying to use Scafender and trying to integrate it natively with CodeCarbon so that we can have per process, so that the estimates could be made more accurate. And ultimately, you should choose the cloud server regions wisely so that okay, sometimes there is you will need to see and make decision between, okay, US Central one is more expensive than US West one, but US West one has less carbon emissions. So should I go with US West one or should I go with US Central one? So these kind of trade-offs will come, but you will need to make a choice, and sometimes choosing environment over money could give you and reap you longer benefits, right? And yeah, spread the community, spread a word in the community about CodeCarbon and related impact that we can have by utilizing this package or making a practice of optimizing our code and paying stress on the carbon intensity. You can reach out to me over LinkedIn or Twitter if you have any doubts with respect to AI or any of the fields like high performance computing, quantum computing, neuroscience, even site reliability engineering, or any sort of technology stuff you want to talk about. And please spread a word. You can use these hashtags and you can just tag me at GreatDevAKS. And that's pretty much it. Happy green coding. And yeah, over to you for QA.
Thank you very much, sir, for spreading this knowledge. All the participants having queries can start filling them or typing them to the chat box.
Do we have any questions? You can please put down your questions in the Zoom chat, and I'll try to answer them as per best of my knowledge. There is a question by Prakash. Since we use a lot of libraries and packages in Python, how to know how much green coded are those packages, right? So that's where like it's again in the AI community, people have started reporting the carbon consumptions in the AI papers. Like if you go to archives, some of the papers which are being produced will have the carbon emissions kind of reported there as to how much carbon emissions were created or produced when the POCs or even the trainings were happening, and how much of it is being generated at the current time with the perfect model in place or the perfect version or the current version of model in place, right? So everyone who has started focusing on this, they have started reporting all these things in their reports. And this is again, when I said that we should be spreading a word in the community about this, what we mean is that as people start growing and start using this, you can say carbon emission tracking model, right? They can start reporting things in their reports, in their publications, so that it is very evident as to how the models actually impact. And that is where I mentioned like CodeCarbon, if you see with the Hugging Face transformers, CodeCarbon, it has a default callback for the trainers, which it has introduced. So if you see the source code of transformer integration, right, it should be having CodeCarbon somewhere. So it has CodeCarbon occurrence, right? And it is actually calling it as a callback, which means if you are using the Hugging Face models, the pre-trained models, they will have something to report on the lines of CodeCarbon, right? So likewise, different libraries are using and have started incorporating the callbacks. Okay, there is a question by Ranjit, whether it will check what type of power mix is available in the cloud region. Yes, it does. And that is something which is being reported by the data sets which the cloud providers are maintaining by their sustainability initiatives. And one thing to note here is that there is a difference between carbon neutral, right? Being carbon neutral or producing zero carbon emissions. So you will see, and again, I'm not tagging anyone here, nor you should be associating this with any of the organizations I'm associated with, but if you see that there is a cloud provider XYZ, right, that is saying that we are carbon neutral, most of these companies are even investing in what we call as carbon offsetting. So what they do is they give X amount of money to some organization for carbon offsetting, and they say that, okay, if we are producing this much carbon, we want you to plant these many trees or do land reforestation for this much area, so that we can compensate. And when they compensate using carbon offset, ultimately they are producing carbon, but they are compensating it by planting trees or doing land reforestation, because of which they come to a null point and they say, as much of carbon is being produced, that much we are reforesting, or that much we are equivalent to that we are planting trees, and that is getting neutralized. That's where people say and companies say they are carbon neutral. So if you were understanding that carbon neutral actually means that these people are not producing carbon at all, that is wrong, right? These people are investing in carbon offsetting, and even local data centers, private data centers, or small startups have investing in carbon, have started invested in carbon offsetting. That is a good thing. But if you try to optimize your code, if you try to choose wisely where to run your code and what mix of hardware or platform you should be using, I think that can complement the carbon offsetting thing, and that should be the primary focus. So carbon offsetting should be the last resort, right? It should not be the primary resort. So it should not be that you keep on exploiting things and then you have carbon offsetting to kind of take care of the exploitations that you do, right? You should be taking initiatives to have the things kind of addressed in proper manner, and whatever is the amount which is going above, which you cannot compensate for, go ahead and perform the carbon offsetting for that particular amount. And in any way, like, you can do it willingly as well. There's no one stopping you to do the carbon offsetting, even if you are not a startup or any other organization. We have another question. Could we say that optimizing the code to achieve less carbon emissions means parallelizing those codes and or using the methodologies of quantum computing? So this is a good question. Yeah, we saw single core versus multi-core comparisons for CUDA implementation, and it clearly showed that multi-core CUDA implementations are much more performant, and they were actually giving the least. And let me go to that graph. Yep. So you see 12 cores, 6 cores, and single core, right? So when you say parallelizing code, it actually means either we are parallelizing the code at the core level. So if we have multiple cores, we have multi-processing done, so that multiple processes can perform the task, and we can have the accumulation or the results collectively kind of stored somewhere. And for that, again, there are frameworks like Python Ray is one of the frameworks which is very popular these days, which is specifically for this particular problem of parallelizing the Python package. And if you are interested, throughout this month until September, I'll be having a lot of sessions on coding distributed applications using Python and Ray framework, even on Kubernetes and different orchestrators like Slurm and Swarm. So if you are interested, you can check out my handle, LinkedIn handle and Twitter handle, and you can register on those sessions, and you will be able to get insights into how you can parallelize the code. Yes, it does mean that parallelizing the code will eventually have more, you can say, you will have the time reduced, and because of that time being reduced, ultimately you will be able to finish the training or finish the compute intensive task in, say, 5 minutes as compared to, say, 20 minutes, because of which less number of compute power is getting utilized, and ultimately you are having efficient usage of your machine, because of which you are optimizing in favor of, you can say, carbon emissions, right? But when you compare it to methodologies like quantum computing, that is a different game altogether. Quantum computing is a very intensive, you can say, field, and that's the results of that should never be compared to the local parallelization or distributed computing techniques that you use, because quantum computing in itself is producing some great concerns with respect to environmental impacts, and that should not be a one-on-one comparison or apple-to-apple comparison, right? Quantum computing is a different game, and we have different measures in place, and this library doesn't work on quantum computing algorithms as such. as of now, like it has not been tried. I'm yet to try it myself, but we never know. And another thing with respect to this particular library, if at all you are using Google Colab, right, which is the collaboration Jupyter platform, it doesn't have, it doesn't report correct metrics, and ultimately it has no provision. The CodeCarbon has no provision to fetch the correct metrics from Google Colab environment in terms of CPU. So CPU training, if you are to do on Google Colab, that should be avoided, because then you will be getting the default estimates. Because if the CodeCarbon package is not able to figure out or read the metrics for CPU or GPU or whatever is the system resource, it makes a choice for a default CPU, default usage, and ultimately it resorts and produces those things. So you will be able to run this package on CPU as the runtime for your Colab notebook, but then the results would be very off from the reality. But it has good support for GPU, and it's purely supported for GPU on Colab. So if you are to do a CodeCarbon training on GPU on Colab, go ahead. With CPU, the estimates would be off, right? So I hope that answered. Will it work properly on Jupyter Notebook? Yes, it does work. It depends where you are running the Jupyter Notebook. So I mentioned if it is AMD or if it's M1 or it's M2, you should run something called as Intel Power Gadget. Let me open it and you will see Intel Power Gadget. And this is just a software-based emulation that you do, that provides you a bridge between your main processor and to CodeCarbon. It will look like that you are running on Intel, but ultimately you are running on AMD, right? So Intel Power Gadget you can use if you are on different systems. But yeah, it supports Jupyter Notebook, and I think the CSV that I showed you has been generated for the training which I did. Is there any trials going to make the implementation to be more optimized other than using Python? Yeah, so as I mentioned, Scaphander is one of the projects which is written as Rust implementation, and that you can see here. That is something which is getting integrated, which will make the model, which will make the working of CodeCarbon more accurate, because ultimately it will be a per process reporting instead of the RAPL reporting system, which reports for the whole system. So if at all your system is being used in a shared manner, if multiple trainings are being run on the same machine, in today's scenario, it is an accumulative accumulative average that you get in terms of power run, right? But if you are to use Scaphander alongside, or if you are able to make it integrate with CodeCarbon on your own, then you will be getting a per process thing, which will be much more accurate. If at all shared training is being used. If it's a single training that you are doing on one machine, then it's sufficient enough. So things are being done to improvise this package, and you can go and check the latest issues as well here. There are support tickets and related issues getting created for different provider support. So as of now, like NVIDIA GPU on Windows, someone has reported this is not supported. So these people should be working on that. So yeah, things are being done in order to make this more accurate. And yep, they are even like getting integrations with some more accurate libraries out there. So electricity map and COT signal are one of those which they recently incorporated. So yeah, that's another thing.
Yes, participants have
nice. So I think it's a wrap. Thanks all for being such an active and good audience, and really want to thank Dr. John and Dr. Christina, for inviting me and giving me this opportunity to interact with such a good audience, and also to speak at this forum, which is of good repute. But yeah, thanks a lot.
We are very thankful, sir, because you actively invited and imparted the knowledge to all of us. So now I will call upon John Paul, sir, to give the vote of thanks.
Yeah, it's my privilege to acknowledge the contributions of fraternity towards this webinar on behalf of the webinar team. Above all, I thank Almighty God for His blessings and grace. I take this opportunity to express our sincere gratitude to Sri Anmol Krishan Sachdeva, Hybrid Cloud Architect, Google, for accepting our invitation and sharing his valuable time to deliver this wonderful session. My heartfelt gratitude to the administrative authorities of our institute, our registrar sir, Dr. M. Radhakrishnan, for constantly striving towards ensuring only the best for every IIIT stakeholder, our director, Dr. Rajiv Daraskar, for instilling a desire to always aim the impossible, our academic dean, professor in charge, Professor Mohanan, for his veteran academic insights, our Associate Dean of Academic Affairs, Dr. Ebin Denilaj, for his pioneering efforts in every activity of the Data Science Research Group, Head of the Department of CSE, Dr. Jayakrishna Sahu, for his consistent support, and other heads of the departments, my faculty colleagues, our technical team, headed by Sri Siju KS, and our student coordinators. With utmost priority, I thank each of the participants for your interest and active involvement. Once again, I thanking you, Sri Anmol, for accepting our invitation and contributed your valuable time for all of us. Thank you, sir. I would also like to take this opportunity to draw your attention towards our exquisite MTech program for working professional in 4 specialization, namely AI and data science, cybersecurity, fintech, big data, and machine learning. The admission for all these programs are currently open. I urge all the interested candidates to visit our website for detailed information and kindly spread the message. And one small note, due to the number of limitations, few of the participants were unable to attend the workshop. So this was a technical, due to the number of limits, those who joined late, they may not be able to join. It was also streamed on Facebook. Thank you for all the support and expecting all your presence in the subsequent sessions of this webinar series. Thank you.
Thank you everyone once again for all the participants for the interactive session with sir and making this an interactive one. I hope to see you all in much more numbers in the further webinar series. Have a great day everyone, and please fill this form, attendance form, which has been sent in the chat box. You will be getting the participation certificates within a week, and yeah, thank you very much.
Thank you all.
Thank you.
Thank you.